So, Vanakkam. So, we will continue our lecture. So, we have been discussing the revision of our subject, okay, so that you will get more clear idea. So, what we have to see. So, we have been seeing the instrument, seismic instrument recording, seismic, the cluster of the equipment instrument, okay. So, how to space that seismic instruments. Okay, so what is the minimum spacing should be maintained? What is the minimum angle orientation should be maintained? Those are all things are the very important which we should know. Okay, so soon after the earthquake, if you look at is the scientific community who is handling recording the earthquake, they release a earthquake report. Okay, so this reports consist of the several things which we have already detailed discussed, but today we will be going to give you a summary of glimpse of that. So the each earthquake report will tell you that where the earthquake is occurred. Okay, so the location of the earthquake, okay, then the nearby cities, okay, so then that earthquake, like what is the isoseismal map, what is the magnitude, okay, so what is the source mechanism, so what was the damage level, okay, is expected, so how many fatalities are expected, this kind of data generally they release. So this comes from the understanding and processing of the seismic wave recorded in the seismic instrument. So if you look at the seismic instrument, it, as we discussed that it records a waveform of the data. So that waveform of the data has been used, okay, so to quantify the earthquake. So the quantification of earthquake, if you don't have the waveform, how do you quantify? Because if you don't have the seismic instrument, which was a scenario in the most of the olden days. As I told that India, the good instrumentation started 1960. Before that, that means there is not proper instrumentation. Even the seismic instrumentation development itself happened only on 1880s. So that means before that, there is no seismic instrument in the world except a Chinese seismoscope. That also doesn't give you the size of the earthquake, it only given the direction of the earthquake. Okay, so people try to quantify the earthquake by some systematic manner. So that is basically the scaling of earthquake, the size of the earthquake. So the size of the earthquake is done qualitatively or non-instrumented way, which is called as a intensity record. So we have discussed intensity record, what are the different intensities are we have, and then how these intensities are useful for this one. So the another way is to get the earthquake sizes using the waveform recorded data, which is quantitative way of estimating the size of the earthquake, and then the instrumental measurement. Okay, this needs a recorded waveform. So depends upon the wave, okay, type, you can get a different magnitude scale, so which we have discussed in detail. So today we will going to give the just a summary of what we have done there in this class. So where you can see that the type of the intensity scale those days used basically as a 6 major category of sizing the earthquake without measuring the earthquake waveform. Okay, so this is how the intensity scales are used. So the Mercalli Cancani Seiberg scale MCS, it has a 12 level used in Southern Europe, and then modified Mercalli intensity scale MMI. So 12 scales proposed in 1935 Wood and Newman, who adapted the MSC scale to the California data set, and it is used to North America and several other countries. Then the MSK, which also again has a 12 level of scale adapted Central and Eastern Europe, and then there is a European micros EMS 12 scale adapted since 1988 in Europe, and its development of the MMI scale. Japanese meteorological scale 7 scale used specifically in the Japan, and road damage intensity scale. This is a new intensity scale developed by my research team, which is specifically used to quantify the damage caused by the road. So all these are no need any seismic instrumented record, and you can see that all this scale, okay, has been specifically modified according to location. So in India, what type of scale, okay, so they use basically, so mostly India they adopted a MSK scale, because this instrument concept itself brought when there was a British was ruling the in India. So basically the British were Europeans, okay, so they brought this kind of measurement. So they use MSK scale in the in the MSK or EMS scale kind of thing. There is a slight variation between this scale. So this scale consists of the 12 level where it is given a description about the. So this we also discussed that the intensity measurements are only report a earthquake which is occurred in the people who are living. Okay, so in the remote area earthquakes, okay, so it may not be noticed because there is no building, there is no human being living. The earthquake in the forest, okay, so earthquake in the sea, okay, without causing tsunami, those are all the earthquakes are not noticed. Okay, so the intensity scale and moreover this is also depends upon the sensitivity of the person who is basically trying to say about the earthquake or scale the earthquake. Some people is very sensitive, they may rate it higher. Some people less sensitive, they may rate it lower. That is what the disadvantage of the intensity scale. You can also see relatively the intensity scale and its the respective damage level. Okay, so you can see that more or less the 12 scales are similar. Okay, so but the Japan scales are slightly different. So most of the scale, the intensity 5, okay, so 5 and 6 onwards you can expect a damage in the building. So that is a comparison, you can take it from here. So that means if you know the intensity value of a particular location, you can know what is the expected damage to the building as it is related to the damage of the building. Okay, so the damage created by the earthquake. So the intensity scale also has a conversion between the intensity to the PGA value or PGV value, depends upon the place to place. This is a typical conversion which is used. Okay, so the acceleration to MMI scale at a particular place. So this is the global comparison of the intensity scale and the respective PGA value in the GALS. Okay, GALS is the unit used in the US mostly. You can see how the intensity scale PGA values are varied drastically, even though the variation is like 6 to 7 is the only one scale variation with respect to intensity, but you can see the PGA variation 32 GALS to 68 GALS. Okay, so 32 GALS to 68 GALS. You can see here 32 GALS to 68, intensity 1 scale. So the twice it's 32 to 147, it's only 2 scale in the intensity. So this is how the scales are comparable. So this will help you basically to assess what is approximately the PGA expected, what is the damage you can expect. So this intensity, individual intensity value observed at each location can be connected together and create a isoseismal map. So intensity map or isoseismal map which is connect a equal intensity at the particular location. Okay, the line is the intensity line which is like a contour line which comes like this based on the intensity recorded at a particular place. So the scientists find that the intensity value reported at a particular location is well matches with the geological formation of the location. Basically geological means rock and soil type. So they observed that low intensity values are reported in the rock area. Okay, the high intensity values are reported in the soil area. So this was the earthquake observations from the San Francisco 1906, which given a initiation of thinking that the soil also plays a major role in the earthquake damage. Okay, so where the origin of earthquake geotechnical engineering is started during those observation kind of thing. This is a typical map. You can see this is actually a geology map which shows a depth of bedrock and then their distribution in the San Francisco. So this is the intensity value observed. You can see there is a higher intensity value to the place where is a more soil thickness. So those intensity scale, whatever, even though it's defined well and used to describe the building damage, useful to convert a PGA, but that only talk about the building, not the important infrastructure which also damages due to the earthquake is the road, which plays a very important role in the evacuation and disaster relief process. So this gap has been identified by my research group, where we put some thought, okay, try to understand how the road damages caused in the earthquake, and that road damages, okay, whatever road damages we are observed, which has been used, and get a road damage intensity scale, as the previous intensity scale does not talk about the damage of the road, okay, particularly, which is again become a road network. So the available road network after the earthquake, okay, and its condition, okay, scaling will help to basically evacuate a people by controlling the traffic, okay, making the own path for the ambulance. So all those things are possible if you have that kind of idea, and description of the road damage and prediction of the road damage due to the earthquake, which has been highlighted by the Unbergen et al. Okay, so where the road damage scale has been developed. So this road damage scale RDS consists of the 5 description. Unlike other intensity, it has a 12, but here we are only having the 5 level of scale. So this 5 level mainly concentrate on the with respect to the road damage description. Nothing to do with observation or not feeling, nothing. Okay, so this is the description, detailed description are given for each one level. So the RDS 1 is actually a very light damage, where you can get basically the road can be used immediately, okay, with a slight cleaning and then doing a small repair work. So the 5 is the extreme level changes, where you cannot use that road at all, it is completely blocked. So the respective, after definition of this, we collected a several data from the past earthquake, where the detailed road damage photos are available, descriptions are available, magnitude are available, distance are available. So that based on those things basically, so we defined this description. This description compared again with the original road reported in the MMI scale. So then you can see that the scale 5, 6, 7 has been used for the RDS 3, 4, okay, so and then the 8 is used for the 5 and 4, which it doesn't basically fit. So that means MMI scale cannot be used, any intensity scale other than RDS scale cannot be used to describe or quantify the road damages due to the earthquake. So that is the message here we want to emphasize. So this further this research group also worked on the data and collected and tried to fit model, okay, the predictive equation for the road damage, okay, has been attempted. So this is a different model. So the research found that the M and D, okay, ED is the epicentral distance, has a very good regression relation and can result a reliable road damage prediction equation. Okay, road damage prediction equation. So among this so many equation, 12, 13, 14 are the equation which is used for, can be used to predict a road damage due to future earthquake. So in fact that will help you to identify the which are the roads are intact, which are the roads are get damaged. So then accordingly you can plan your traffic movement, okay, so and then ambulance movement, evacuation process, all those things. So the problem associated with this kind of non-instrumented data measurement is actually, as we told, that it depends upon the sensitivity of the person, and then looking at the cracks, okay, and then the description of the damage at particular person. So there is no universal description. Some people may count some point, some people miss some point, so which is basically not appropriate. In case the earthquakes are happening in the remote areas where there is no people, no house, so even though the earthquake may be strong, since there is no people to feel, there is no building to damage, then those kind of earthquake it may not be there. But however, these scales are very important because most of the historic earthquakes are having the isoseismal map and intensity values, which are very important basically to plan for the your earthquake hazard value prediction in form of the intensity level, or you can take estimate intensity and try to convert into the peak ground acceleration, peak ground velocity. There is some equations are available on for this kind of things. So in order to overcome this, scientists thought, okay, so then they come up with the concept of magnitude. Okay, so the magnitude was actually size of the earthquake, which is estimated, okay, which is arrived based on the waveform recorded by the seismic instrument. Okay, so the waveform recorded by the seismic instrument is used to arrive a size of the earthquake, that is called as a magnitude. Okay, so this was actually come from the concept of Teller magnitude, where people used to arrive size of the planet using its brightness. Okay, so the similar way the wave, okay, the wave amplitudes are bigger, the magnitude will be bigger. The wave duration, okay, is a bigger, smaller, depends on that, the magnitude will changes. So initially the Richter created a first magnitude scale, so which is called as a Richter local magnitude. Okay, from the California earthquake. So where they will record data like this. Okay, then identify a different type of wave as we discussed earlier, and then take a amplitude in mm. You can take this and then put it in the scale, and similarly the P and S wave difference here, then connect it, then you will get a magnitude of the earthquake, or you can even use this empirical formula to get a magnitude of earthquake. So here they used to highlight that the highest amplitude of the wave. So in general the P and S wave is the most nearly recorded data, and the S wave will have the highest component. That means the Richter magnitude scale is more up valid for the S wave kind of waves. So the then sometime if you don't have the proper this S wave recording due to long earthquake or something, people used to other local magnitude which is basically used within the region. Okay, so the duration magnitude MD, microseismic magnitude MS. So these are all the local magnitude people use to get a size of the earthquake. Here we should remember that, so this local magnitude varies with region to region. Some seismologists used to practice this kind of thing, MD and MS. So but this, okay, when you have the very big earthquake very far away, so your broadband station may record, but you may not have the your higher value as a P and S wave component. Okay, so in that case the body wave, okay, and surface wave, which is created body of the earth and far away earthquake in the surface, okay, are used to get a magnitude which is called as a teleseismic magnitude MS and MB. So they use the surface wave of the earthquake, okay, and then the P wave of the earthquake. So this is like a typical example how the MS equations are given. So you can also see the time duration and period kind of things from here. So this, if you feed that, you will get a this one. This was actually developed based on the the amplitude of the Rayleigh wave by the Kutzenberg and Richter. So the body wave magnitude, so that is the surface wave magnitude. The body wave, this is basically the body wave amplitude and the time, okay, has been taken into account, and then the body wave relations are given. So which is useful when you have the predominant record of the body wave. For example, when you are in the shadow zone of S, okay, so the S shadow zone, shear wave shadow zone, so you get a body wave. So using those kind of deeper transformed seismic energy, you can get a body wave magnitude. Okay, so the scientists observed the same earthquake, the body wave and S wave and then the surface wave magnitudes are uniform. It is obvious that, as we have seen in the wave propagation, that the amplitude and the duration of the particular ground motion at a recorded site depends upon the distance and the magnitude of the earthquake. Okay, so and then where it occurs and how big it is, all those things. So this phenomena not having the equal magnitude at the same earthquake is called as a magnitude saturation. Okay, so where after some time the magnitude remains constant. So which was identified in olden days by the seismologists. People try to basically get this information. Okay, so then see that the estimations are not in the saturation zone, but it is non-saturation zone. So this is how you can see the magnitude, different magnitude, a true magnitude and measured magnitude. So you can see that these magnitudes are basically constant after reaching some point, particularly MS, MB, it has its own value of the constant values. So what causes saturation? As we have seen in the seismic wave propagation, okay, the waves are originated depends upon the fault fracture. Okay, so the larger the fracture, the larger will be the wave amplitude. But since it travels a very long distance, okay, the distance from the origin of the earthquake to the your station, also very important. The rupture happens in the fault, also very important. These two has been considered, and this is the responsible to decide the magnitude saturation or not. Okay, so the magnitude saturations are so very important aspect. One has to know what magnitude maximum that particular magnitude is applicable. Okay, you cannot be using all the scale in all the place. So in order to overcome this kind of magnitude related things, which is the function of amplitude of the seismic waves, so people come up with the concept called seismic moment. Okay, so the seismic moment, the stiffness of the rock and then the slip produced by that is taken into account, then they estimate a moment of the earthquake. So using this momentum, okay, one can estimate a magnitude that is called as a moment magnitude. So the moment magnitude is very recent, so which works for all the range of magnitude, okay, starting from 2 to 10, and then it also the ambiguity in the measurement of like this Richter, because Richter said that beyond 100 kilometer you have to apply some kind of factor and all. So those kind of discrepancies are not there. The moment magnitude scales are very good and can be used for the any this one. So at the nutshell, so we have studied a magnitude, okay, quantification of the earthquake, such as a intensity values, and then the after intensity value RDS has been developed. Okay, so then other RDS, the magnitude come into picture. So then you will have the different local magnitude, body wave, surface wave, moment magnitude. So all these magnitudes are related to each other. You can also have the relation between the intensity and the magnitude, which you think you have the sufficient data, will be useful for basically making some kind of prediction equation. So here you can see the summary type of the wave and symbol, and then the wave pattern, and then the period at where it is being recorded so far. Okay, so this is a conversion equation. Basically the converting magnitude, because as we have seen that Indian any region earthquake started from the historic times where the isoseismal maps are kept. Okay, then followed by you will have the instrumental record where ML, MB, MS, MW has been kept. So there is always need for homogenizing the data by removing all this ambiguity and make that all of them in a particular scale. Okay, so that process is called as a magnitude conversion. You get the typical example shows how the moment magnitude and the magnitude of the earthquake, how it is related. So the another important aspect, okay, in the this one is actually intensity, magnitude in the earthquake measurement is the seismic energy. So when the earthquakes are occurring, how much the energy has been released. Okay, so that is basically the measure in terms of joules. Okay, so where the surface wave MS and E is the minimum. Basically this will give you the idea. Okay, so the how much energy released at a particular place. There is a empirical correlation between the E and MS directly. So that will help you in that. So using this understanding of the energy, people try to see the global perspective on the different earthquake occurred in the world. So this basically gives the earthquake size based on the magnitude of the earthquake. Okay, you can see minor, light, moderate and strong earthquake, and major and great earthquakes. Okay, so then the notable big earthquake in the world, you can see all those earthquakes. Then the notable human activities. Okay, notable human activities. Okay, so which you can see that there are many troops are entering on this, even though they are killing, but still the tension is going around the world. You should aware when you are watching this video, basically there was an issue with the getting a top portion or wave recorded in that. So because it is the you didn't get, we added that. Okay, so that is about the earthquake energy. So the earthquake energy plays a very important role. In this graph you can also understand that the number of earthquake per year. So you can see that the low size magnitude, minor earthquakes are very large number, up to 12,000 per year. So 1 lakh, 10 lakh, 12,000. The larger magnitude generally occurs very rare. Okay, so the moderate magnitude occurs considerably on all the region of the world. Okay, so this energy release also related to the explosion of the particular location. So you can see the energy released by the equivalent magnitude and then the explosion required to create a similar kind of energy. So since it needs a lot of explosion to create a magnitude, that is why the earthquakes are not really created and did for measurement as well as the analysis, okay, in the model studies like other subject. Okay, so but you can get the computer based data and do the analysis and modeling purpose, that is very widely practiced in the several places. So you can see some of the atomic bomb area, how much the kg explosion which is equivalent, what is the magnitude on the this side. So this is like atomic bomb where you can see how much the magnitude and what is the equivalent magnitude and what is the loss, okay, due to the. So this kind of the important aspect can be obtained from the this graph. Okay, so this graph will be useful to know the energy released and how this energy is strong, how many kg of explosion if you do, you will get a similar kind of seismic energy. So this is about the earthquake sizing. Okay, earthquake sizing or estimating the earthquake magnitude. There are very few people do research on this area in our country, which has a very good potential for extend several things. So we have very limited homogeneous equation to convert intensity to the magnitude, and then we have less intensity predictive equation with respect to the PGA as well as the spectral acceleration for considering the entire Himalaya as a different segment. Okay, so this kind of information basically helps to identify the how the human activity based seismicity, natural based seismicity is going on. Okay, so this is what we discuss in the earthquake size. Okay, so we have seen that intensity as the one of the scale, magnitude is the one of the scale. So this has been widely used. Intensities are measured non-instrumented way of quantifying the size of the earthquake. Magnitude are the measured and having the proof to estimate a magnitude size. Okay, and then number of earthquake happens on the each size per year also we have discussed. So these informations are useful to quantify, to size the earthquake at a particular location. So these informations are further we can use for the other chapters and application. So now after studying the GMPs and predictive equation, you will be clear what is the intensity, magnitude, how you can use it in the seismic hazard analysis. So with this we will close our lecture. Okay, so thank you very much for watching. We will be continuing our lecture in the next class. Thank you very much.